right, welcome everyone. Today is Monday, January 10th, and it is 10:15 a.m. in Mountain Time, which is the time we should have been in Salt Lake City today. Haley, you can go ahead and end the slide share. So it looks like I've got a setting mistaken, which is that the chat is open to everyone. So just so my panelists know, you probably shouldn't type anything in there that you don't want everyone to see. But that's okay. We're going to go ahead and get going. So welcome to the first press conference of what was supposed to be the 239th meeting of the American Astronomical Society. We had to do a hard pivot there, but we are all here and we're excited to be here. This topic is going to be galaxies and quasars. My name is Susanna Kohler. I'm the AAS press officer, and I am joined by co-hosts here. We've got the AAS deputy press officer, Kerry Hensley. We have the AAS media fellow, Haley Wall, who is a graduate student at West Virginia University. And we have the Astrobites media intern, Macy Huston, who's a graduate student at Penn State. And so the four of us will be your hosts for the week. And we're looking forward to a good program. Now, I knew that this meeting was going to be a little bit different, seeing as these press conferences are the first in quite a while to not be organized by the illustrious Rick Feinberg, our former AAS press officer. But I didn't realize that this was going to be, to my knowledge, the first set of AAS meeting press conferences not accompanied by a AAS meeting. So we are adapting. And we're really excited that we're still able to bring you this press program. And the fact that we're here, despite the very short notice cancellation of everything, is a tribute to the very hard work and amazing flexibility of all of our presenters this week and all of their public information officers. So thank you so much, all of you, for being here. And thanks to our audience for being here. So without further ado, I'm going to go ahead and get started. For those of you who haven't been to one of these before, a few ground rules. So first off, note that this is being recorded and being live streamed to YouTube. And you can find the recording of this on our YouTube channel, the AAS Press Office YouTube channel later. And the way this is going to work is that the MC in this session, that will be me. I'm going to go ahead and give a brief introduction to the topic. I'm going to introduce the panelists and give their presentation title. And then we're going to go ahead straight into the presentations. All of the panelists will speak in order. And then after that, we'll go to the Q&A session. And so at that point, they will answer all of the questions that you have for them. If you want to submit a question, if you're watching this on Zoom as opposed to on YouTube, there's a Q&A box at the bottom of your screen, a button that you should be able to click to submit a question. When you do so, please make sure that you indicate your affiliation and your name and who the question is for. And so those will go into the Q&A queue. And at that point, you can upvote questions if it's a question that you have as well. And then when we get to the Q&A session, we will go ahead and Kerry will read those in order from that list. And at that point, the speakers can answer them. So we have asked the speakers not to answer the questions during the presentations, so not to answer via writing, because this is being streamed to YouTube, as mentioned, and those folks won't be able to see the questions that are being submitted. So we'll make sure to read them all out loud at the end. All right, so without further ado, we're getting started. Again, this is the Galaxies and Quasars session. And the lineup we have for you today is first, we've got Jessica Sutter from University Space Research Association, USRA. And she's going to be talking about a map of the molecular ring and arms of a spiral galaxy. After that, we've got Yuanze from Johns Hopkins University. And she'll be presenting a multi-wavelength view of IC 860, what is in action inside quenching galaxies. Then Ryan Hickox from Dartmouth College will present Uncovering a Hidden Mini Monster, a heavily obscured active galactic nucleus in a dwarf star-forming galaxy. And lastly, Mallory Molina from Montana State University will present a new population of supermassive black holes in dwarf galaxies. And note that we will be putting all of the press releases and the presentation slides associated with all of this in the press kit online. So with that, let's go ahead and get started. Jessica, take it away.
Okay, thank you so much for giving me this opportunity to share the work that my colleague at the University Space Research Association, Dr. Dario Fata, and I did to measure the singly ionized carbon emission from a nearby galaxy. Oops. So before I get started, I want to talk a little bit about why we might be interested in measuring the singly ionized carbon, or C+ emission. Throughout my talk, I'm going to use this bracket C2 to represent the C+ emission from this galaxy. So when you see that, know I'm referring to the 158 micron line of singly ionized carbon. This C+ emission is really important because it's one of the major cooling channels the interstellar medium, or the ISM, has for cooling down after it's heated by young stars. So in this simple model of the star-forming region in a galaxy, we have young O and B stars heating up the gas through emission of high-energy ultraviolet photons. In order for thermal balance to be achieved, we need things like singly ionized carbon to absorb and re-emit that light in longer wavelengths that can escape the interstellar medium, like this C+ 158 micron line. So the C+ line is really important, both because it's this cooling channel for the interstellar medium, and because there's reason to believe that because of that, we could potentially use it to measure star formation in galaxies. Since if heating is caused by young stars and cooling is done by C+, and there's a balance between heating and cooling, we expect C+ heating to trace young stars. C+ is also really interesting because it's often the brightest emission line observed in galaxies, which makes it detectable both in the local universe and in the high redshift, very distant universe, as shown by these two Z of approximately 7 measurements of the C+ line. This means that it has potential to be used as a star formation rate indicator across cosmic time, which would help us understand how galaxies grow and form throughout universal history. Unfortunately, there are still quite a few unknowns about the C+ emission. One of the main ones is characterized by something called the C+ deficit, and is shown in this graph here, where we have this ratio of C+ emission to far infrared emission plotted as a function of galaxy brightness. And what we can see is there's this pretty clear decreasing trend in this ratio as galaxies get brighter. This is a problem because we know infrared luminosity traces heating in a galaxy. So if there was that nice balance between C+ cooling and young star heating, we would expect this ratio to be flat, regardless of how bright your galaxy is. Of course, that's not what we see. We see this decreasing trend, which tells us that something's happening in the bright galaxies that makes C+ a less efficient coolant of the ISM and maybe not quite as accurate tracer of star formation. If we want to be able to use the high redshift measurements of C+ to determine how galaxies are changing over time, it's really important that we understand what's causing this deficit behavior. In order to do that, one of our best tools is currently the Stratospheric Observatory for Infrared Astronomy, or SOFIA, which is shown here, and is one of our best methods for measuring the C+ line because it can fly above the water vapor in our atmosphere that otherwise blocks this emission from reaching us, and map the C+ emission in nearby galaxies. So that's the work I did with Dario Fata. We looked at the C+ emission from across the disk of nearby galaxy NGC 7331, often referred to as the Milky Way's twin because of its similarity in structure and star formation rate. NGC 7331 was an interesting target because of its strong molecular ring as well. So we could see how this infrared bright ring looked different in C+ than potentially the center, the core and the disk of this galaxy. It's also interesting because it's one of the few galaxies we've mapped at singly ionized carbon that's not face on, but we're instead seeing it at an angle, a very high angle of 72 degrees, which allows us to test how our observing perspective also affects our measurements of the C+ line. With our map of the C+ emission across NGC 7331, we were able to study where within the galaxy the singly ionized carbon emission was coming from. One of the measurements we were able to make was to determine what fraction of our C+ emission was coming from neutral phases of the ISM, where hydrogen is neutral, and what fraction was coming from ionized phases of the ISM, where hydrogen is ionized. And this measurement is really important because we believe that star formation cooling balance should mostly happen in the neutral phases of the ISM. So the C+ emission from the neutral phases is likely more closely tied to the star formation than the C+ from the ionized phases. And what we found when we measured this ratio, which is plotted here, 1 in this plot would be 100% of our carbon emission coming from the ionized phases, 0 would be 0%. And we've plotted it as a function of radius, so 0 being the center of the galaxy and then moving out as radius increases. We can see that there's a slight trend in this fraction as we move out in the galaxy. In the center of the galaxy, we're closer to 50% of our carbon emission coming from the neutral phases, whereas in the disk, we get up to approximately 90% of our C+ emission coming from the neutral phases. So in the center, C+ might not be really tracing star formation as well as it is in the disk of this galaxy. We were also able to see how our observing perspective affects our measurement of C+ emission by splitting our data points up into those that come from the far side of the galaxy and those that come from represented by the blue points, and those that come from the near side of the galaxy represented by the red points. Because this galaxy has a ring and because we're seeing it at an incline, when we look at the far side and when we look at the near side, we're seeing two different parts of this galaxy. So if we think of the molecular ring of this galaxy kind of like a donut, we can think of on the near side, we're seeing the outer edge of the donut. Whereas on the far side, we're kind of seeing the inner edge of the donut around where the donut hole would be. So we're seeing two different parts, and we can see that based on the split between the blue points, which are measuring the far side or the inner part of our donut, and the red points, which are measuring the near side or the outer part of our donut, the near side has a systematically higher fraction of the C+ emission coming from the neutral phases than the far side, which informs us that our observing perspective can affect where within the interstellar medium the C+ emission we measure is coming from. With this map, we were also able to extend measurements of the C+ deficit into less infrared bright local environments inside of NGC 7331 and see how this trend is affected by these local conditions. So in this plot here, I've again shown, this is similar to that earlier plot where we have the C+ luminosity over the infrared luminosity, so the C+ cooling over heating measured by infrared as a function of infrared brightness. And we can still see that decreasing trend. We still see the C+ deficit. But what's really interesting is we now see this kind of smooth continuum from the ultraluminous infrared galaxies measured by the gold sample and shown in these blue points into the less infrared bright disk and arms of NGC 7331 shown by the colored points here. So this tells us that whatever is causing the C+ deficit is occurring both in a global scale in these ultraluminous galaxies and on the local scale within the disk of NGC 7331. So with that, we were able, just as some quick conclusions, we were able to use this C+ map of the Milky Way's twin, NGC 7331, to test how local conditions within NGC 7331 affect the strength of the C+ emission. By observing this highly inclined galaxy, we were able to see how our observing perspective can affect the strength of this emission line, which is important to know as we try to use these high redshift measurements of C+, where we might not know our observing perspective since it really just looks like those distant galaxies really just look like a single point. We were also able to see how the local environment C+ deficit has this smooth continuous trend from the ultraluminous infrared galaxies in GOLS into the local environments that we measured. And we were able to see the bright C+ emission from this ring. In order to really understand how we can use these C+ measurements to understand the interstellar medium across the universal history, it would be great to have more of these resolved maps of nearby galaxies so we can really see how the interior conditions in a galaxy, the interior structures and properties affect the strength of this emission line. My contact information is up on this slide, and I just again want to thank you all for giving me this opportunity to share our work.
Okay, Yuanze, if you want to go ahead and get started.
Okay. Hi, everyone. I'm Yuanze, a graduate student from Johns Hopkins. The title of my presentation today is a multi-wavelength view of galaxy ICE60. Through this case study, we wish to answer what is in action inside quenching galaxies. This work is supervised by Dr. Rowlands and Dr. Alatalo from Space Telescope Science Institute. First, what are quenching galaxies? If we take a snapshot of all galaxies today and sort them based on their stellar mass and color, we would find that they predominantly fall into two groups. One is the blue and star-forming group, and the other one is red and quiescent, not star-forming group. Over cosmic time, we observe an increase of galaxy number density in the red group and a decrease in the blue group. This promotes a galaxy evolution scenario that galaxies are evolving from the blue group to the red group. We define the word quenching as a decline in the rate of star formation, and the quenching galaxies thus refer to those that are currently undergoing this transition. One of the big picture questions we're trying to answer by studying these galaxies is what's stopping the star formation. One natural way to think of this is galaxies need to lose gas, because if there's no gas, there's no fuel for star formation. One of the many ways the galaxy can get rid of gas is related to their central black holes. The central black hole can become active and be an active galactic nuclei, or AGN, and drive a powerful outflow that expels the gas out from a galaxy. But we have found large amounts of cold molecular gas in some quenching galaxies that challenges this traditional view, and that's why I put a question mark on the slide title. So a possible alternative picture is that the black hole disturbs the gas rather than expel them with a much weaker outflow. So to better understand what's actually going on in these quenching galaxies, we look into one of them. IC60 is for which we have exquisite multi-wavelength data that allow in-depth investigation. Here's an overview of some of the main data results we're using. First, we have the optical integral field spectroscopy data, which provides visually resolved spectral information that allow us to derive the kinematics of stars and ionized gas. Then we have the interferometer data from gamma array observed at millimeter at radio that provide information of the single molecular gas. And then we have the Hubble Space Telescope, which provide high resolution multiband imaging from near UV to near IR. Here, I try to summarize the findings we have for what's going on in this galaxy. So here we see a CO intensity contour overlaid on a Hubble image. We see that the molecular gas is very centrally concentrated, and this actually suggests an external origin of the gas and a possible recent merger. Then here is the composite three-color image from Hubble observations. We clearly see that this galaxy is a barred spiral, but there is a third spiral arm hanging there, and we suspect this is a possible tidal feature after merger. And overall, in this image, the optical color of the galaxy is very blue, which suggests the galaxy is at an early stage of transitioning, and it's promising that it still contains the evidence of the triggers for the important transition. And last here is the V-band Hubble image, to which we applied unsharp mask to highlight the dust features. First, at the exact center of the galaxy, we observe a compact radio emission that's consistent with being produced by an AGN. And the dust filaments here trace the shape of a cone, indicating there is an outflow going from the center of the galaxy. One component on which we want to give more detail is about outflow. We actually observe multi-phase outflows in the galaxy. So from the sodium D molecule doublet absorption, we see the evidence for neutral gas outflow. Here is a spectrum of the absorption, and the red component here is the blue shifted signature that's characteristic of an outflow. This spectrum is taken from the blue beam here on the left, and it sits right on top of the dust cone. The molecular gas outflow was first observed by a previous study, and here we also see evidence of it in our CO data. So here in the position velocity diagram of our CO data, we find there is a small blob of gas offset to the center along the minor axis of the galaxy that has motion that's deviating from the bulk motion of the gas. And this small blob is likely the outflowing gas. Further investigation on the properties of the outflows suggests that these outflows are not very powerful. They either only contain 4% of the total molecular gas in the galaxy or has a relatively small mass outflow rate. The velocities of these outflows cannot support the gas to escape the galaxy. So finally, as a summary, what do we find inside this quenching galaxy? We find evidence of merger history and agent activity, and we find presence of multi-phase outflows, which are not powerful enough to expel gas out of the galaxy. Important implications include that outflows disturb the gas to prevent star formation rather than expel the gas. An agent does play a role in galaxy quenching, but it is still hard to say whether it is driving the change or is just there along for a ride. More investigation is needed. To summarize in a sentence inspired by Ellis' poem, so star formation ends not with a bang but a whimper. And that's all. Thank you.
All right, hi everyone. Here. Oh, that's the wrong desktop. Just 1 second. So share. Screen. There we go. Great. Hi all, I'm Ryan Hickox from Dartmouth College, and I'll tell you today about uncovering a hidden mini monster, a heavily obscured active galactic nucleus in a star-forming galaxy. And this
Ryan,
work, oh, yes.
Just before you go, we're not seeing a slide right now.
Oh, yeah, it's doing a weird thing. Sorry, thank you.
Nope.
I go to share and I click on the one I want to share, and then it's not sharing it. Just a second, stop share. Let me try one more time. Share screen, desktop, share. Okay, there we go. Is that working now?
Perfect, yeah.
Okay, sorry about that, everyone. Again, I'm Ryan Hickox, hi. And so I'm going to tell you about this obscured AGN in a dwarf star-forming galaxy. And this is actually work that was done by Jack Parker, who graduated from Dartmouth College last year. And this was his senior honors thesis. And so some excellent work by him and his work that we are aiming to submit for publication soon. And it was done using observations from the Chandra high resolution camera guaranteed time observation team. So the question we're trying to answer, the basic question is, what is the origin of supermassive black holes? So as everybody on this call probably knows, every massive galaxy, or pretty much everyone, has a supermassive black hole in the center, but we don't know where they came from. The first ones that we see early in the universe, we actually see black holes that are 1 billion times more massive than the sun when the universe was less than 1 billion years old. And so this is a conundrum as to how they formed. And as structure forms in the universe, there are multiple different pathways that one can imagine that would create these first black holes. So this diagram gives you a sort of basic schematic of what those scenarios are, and they produce black holes with different masses. The first one is a stellar remnant. We know that when massive stars blow up, they leave behind a black hole at the end, and that could happen in the early universe. So you have gas cooling into a disk, massive stars form, and we know that stars are pretty big, so you could end up with a black hole that's quite large, something like 100 times or so the mass of the sun. You can also have a process where some gas in a galaxy gets funneled down to the center of the galaxy. You form lots of stars there, and there's actually gravitational runaway that causes all of that to merge together and leaves you with a black hole of about 1,000 solar masses or so in mass. But the third process, so those are runaway collisions. The third process, and maybe the most exotic of these, is direct collapse. The idea that you have an early galaxy that becomes unstable all over the galaxy, a large amount of mass collapses down towards the center, and then a black hole forms down there in the middle and basically eats up all this material. And so there you can have a mass of 10,000 or even 100,000 solar masses that form straight away from this direct collapse scenario. And previous work has seemed to suggest, and I'll get into this a little bit later, seems to suggest that the direct collapse model may actually be the leading one for how these early supermassive black holes formed. But the work I'm going to show you today suggested maybe it's not that clear. And indeed, some of these other processes almost certainly are still allowed in certain scenarios. So how do we study this? How do we actually learn where these supermassive black holes came from? Well, the obvious thing you could do is look to the distant universe, look at very distant galaxies where the light from them has taken a long time to reach us, and actually watch the galaxies where these black holes are forming. And we're on the verge of being able to detect these galaxies. So everybody's excited about Webb. It's fully unfurled now, super exciting. And Webb will, this is a simulated image from Webb, Webb will be able to detect very distant small galaxies in the epoch when these black holes are forming. And so we're sort of beginning to take the steps of actually directly observing this process. However, those, even if we do detect them with Webb and with upcoming observatories, those are distant, faint, and challenging to study because they are so far away. And so another technique that has been developed over the last decade or so is to look in our backyard, look at dwarf galaxies, nearby galaxies, small ones, say with 1 billion solar masses or less, so hundreds of times or less stellar mass than the Milky Way, and to look at the black holes in them. And they're interesting because they have grown relatively little compared to their more massive relatives over the history of the universe. And so it's not entirely pristine, but they give us some picture of what may have happened early on. Now, how does this tell us about the black hole seed mechanism? Well, the direct collapse scenario gives you massive seeds. That's a rare process. And so if that happens, you would expect relatively few, less than half, maybe well less than that, of dwarf galaxies to contain massive black holes of, say, over 100,000 solar masses. But if the black hole seeds form from stellar processes where they start light and then somehow can grow up rapidly from there, then you might expect the number of black holes to be larger, or the number of galaxies with black holes to be larger, because this is a very common process. We expect, stellar remnants to exist in every galaxy. So we can do this and look at dwarf galaxies, but this is tricky because, whoa, what happened to my little video there? There it is. This is tricky because black holes in dwarf galaxies are hard to find. The light from these black holes can be swamped by that from the galaxy. It's a small galaxy, but it's also a small black hole. And so the way we can find them is by looking for the light produced by black holes that are accreting surrounding material. This is an active galactic nucleus, so sort of a small version of a quasar. And the next presentation by Mallory and Molina will also tell you some more about that. And so in particular, these AGN growing black holes are really good at producing X-rays. So the idea is, let's look for X-ray signatures of this. So we did this. We targeted 8 galaxies with the Chandra X-ray Observatory. These are ones that have some kind of tentative evidence from visible light observations that they might have a growing black hole in there. But if we see X-rays right down in the middle, that gives us more evidence that indeed there is a growing black hole. And so we targeted these 8, and of only one of these actually did we see clear evidence of a black hole, and that was this one, Markarian 462. So here's Markarian 462 in context. It's actually outside a little compact group of galaxies. If we zoom in on it, there's a Sloan image of what it looks like. And if we take an X-ray image, zoom in on that, we see a point source right down at the center. So this is where Chandra's exquisite angular resolution is really useful. We can tell exactly where the source is, and it's right at the center of the galaxy. And an indirect estimate of the black hole mass of this thing says it would be about 200,000 or so times the mass of the sun. So it's a very low mass supermassive black hole, or a very heavy, what we would call intermediate mass black hole. So we observed this, but we found 2 surprising things about this black hole. So one thing, we know there's a black hole there, but 2 surprising things. One is that there are more high energy than low energy X-rays than what you would normally expect from one of these things. So it's actually producing a lot of high energy X-ray emission relative to a typical growing black hole. And the second thing is that overall, the X-ray brightness is less than you would expect, given the signatures that we also see in the visible and the infrared. And so if we combine these 2 things together, it suggests that the low energy X-rays are actually getting suppressed by some material that is absorbing them. And so we think this is a heavily obscured black hole that's obscured by intervening material. And so the picture may look something like this, where we're looking through a dense cloud of gas at the center. And so this is one of the first, we know that big growing black holes, the majority of them are indeed heavily obscured like this. But this is one of the first ones that we've seen where we have really strong evidence from particularly X-ray observations that they're obscured in a dwarf galaxy. So that's exciting by itself. But also, this is exciting because these sources may represent a new type of object. If indeed there are a lot of other obscured black holes that are growing in dwarf galaxies, then they might be missed from the previous surveys, in particular X-ray surveys or say visible light surveys that we use to identify these things. And so that could indicate a much larger population of massive black holes than we initially thought about. And so this, of course, could have implications, as we discussed before, for how the first black holes formed in the early universe. It also tells us how these black holes are growing now and may give us some clues as to whether these central black holes have an important role to play in the lives of dwarf galaxies over the history of the universe. So that's all we have for now. I'd like to thank the NASA and the NSF for support for this work, and thanks to the Chandra Press Office for putting together a lovely press release for us. Here's my contact info, and I look forward to answering any questions. And thank you very much to the AAS for putting this up. Thanks.
Hi, everyone. My name is Mallory Molina, and I am a Ford postdoctoral fellow at Montana State University. And today I'm going to be talking about my work studying a new population of supermassive black holes in dwarf galaxies. So even though we talk about galaxies as being a single object, they're actually a collection of many different objects which will reside in different parts of the galaxy. Outside of the center, you'll have stars, dust, and gas, and those are the dominant matter components of any galaxy. Meanwhile, in the center, you have a supermassive black hole that resides in almost all massive galaxies. However, one of the really big unanswered questions in galaxy evolution is how did those first black holes form in the early universe? Now, unfortunately, we can't just go and directly detect the first generation of black holes in the early universe, because we only really detect the total or integrated light from early universe galaxies. And that's what this image here on the right is showing. So if you look at these points of light with Z values next to them, those points of light are actually entire galaxies. So they hold all of the stars and the dust and the gas that we talked about. So in order to confidently detect an active black hole in these galaxies, it would need to be so bright that it outshine the entire galaxy. And we call these black holes quasars. And they have masses of 1 billion solar masses or more. So they're really way too big and are too evolved to help us constrain that first generation of black holes. So instead of looking in the very distant or very early universe, we instead rely on supermassive black holes in nearby dwarf galaxies to give us clues about the first generation of black holes. So if you look at the image on the right, you'll see that I've circled 3 kind of splotchy looking galaxies. And these are actually local dwarf galaxies. And just by looking, you can tell that they are physically much, much smaller than a typical Milky Way-like galaxy. And on average, dwarf galaxies tend to be around 10 to 100 times smaller than the Milky Way. And this is because they really haven't interacted with other galaxies as much over cosmic time. So if a black hole exists in these objects, it should have a very low mass, very similar to those first generation black holes. And in fact, the typical mass found in dwarf galaxies as of now is around 100,000 solar masses, which is a lot smaller than the million solar mass black holes that you find in Milky Way-like galaxies. However, because these black holes are smaller, that makes them less luminous and therefore harder to detect. And I like to think about this kind of as a spotlight and flashlight scenario. So traditionally, when we look for optical signatures of black holes, we look for black holes that can outshine their host galaxy. So if we consider the host galaxy the spotlight and the signal from that active black hole a flashlight, then the spotlight needs to be relatively dim and that flashlight needs to be relatively bright for us to be able to detect that signal. However, if that flashlight is weaker or if that spotlight is brighter, then we lose the signal from the flashlight or we cannot see the signal from the black hole. And so in this scenario, in terms of the actual galaxies, you can think of this as being the star formation is increased, which effectively hides the signal from that black hole. And since most dwarf galaxies are actively star forming, this causes a real problem. And so one of the big questions that we want to figure out is there a way to cut through that star formation and find black holes in these dwarf galaxies that we can then use to constrain the origin of supermassive black holes? And so to help answer this question, I have developed a new technique relying on the coronal line iron-10 6374 to search for black holes in dwarf galaxies. So if you look at this image here on the right, this is an example of a dwarf galaxy in my sample, and this is the iron-10 6374 emission line for that galaxy. Now this line is pretty special as it's created by the hot X-rays in the corona surrounding an active black hole, hence the name coronal line, or by outflowing winds from a black hole. And additionally, it needs very high energy photons that are not easily produced by stars. So if you see this line, it's a pretty good indicator that there's a black hole present. So if we consider our spotlight flashlight analogy, here, even if the spotlight is very bright and you have a lot of ongoing star formation, the flashlight or your detection method for a black hole is a different color, so you should be able to spot it over the spotlight. Now, I was actually motivated to do this study by the detection of iron-10 in the spectra of two previous black holes. The first was the black hole in J1220-3020, which is shown here on the left. It was identified by its strong radio emission by Yuanze et al. In 2020, and then I detected the iron-10 line in my first 2021 paper. The second is Markarian 709 South, which was radio detected black hole by Yuanze et al. In 2014, and then we again detected the iron-10 line in a 2021 paper here. So this means that there were two objects, both of which had their black holes missed by traditional optical techniques, and both had the presence of this iron-10 line. And so this led me to wonder, could I actually use iron-10 to help find black holes in dwarf galaxies that would otherwise be hidden by star formation? And to answer this question, I led the first systematic search for iron-10 in dwarf galaxies. So to do this study, I relied on optical data from the Sloan Digital Sky Survey, and I was able to identify 81 black holes in dwarf galaxies that were detected by their iron-10 emission. And this work has been published in the Astrophysical Journal, and the information is there on the bottom. So for all of the objects in our sample, almost all of them had iron-10 emission that was too bright to be explained by stellar processes, such like supernovae or novae. However, the iron-10 emission was consistent with an accreting supermassive black hole, or a black hole that was actively eating material. In addition, about 50% of those 81 objects showed additional signatures of black hole activity, either in the radio, X-ray, or optical bands. And so this work basically showed that iron-10 can be used to search for black holes in dwarf galaxies. So after we had finalized our sample, we then looked at the properties of the galaxies that were hosting these black holes. And so here you can see the optical images of all 81 host galaxies in our sample. And if you look at the images, you can see that they're different in many ways. They're different sizes, shapes, some are inclined, some are face on. But one thing that they all seem to have in common is their color. They all look pretty blue. And this blue color indicates a lot of active ongoing star formation. And in fact, we can quantify this by looking at the galaxy color versus galaxy mass diagram shown here. And so if you haven't seen one of these before, if you're up at the top, you're a redder galaxy and you have lower star formation rate. And if you're at the bottom, you're a bluer galaxy and you have a higher star formation rate. And then galaxy mass increases from left to right. So if we look at traditionally optically selected black holes in dwarf galaxies, they tend to be pushed towards the more massive red end of the galaxy black hole population. However, the iron-10 selected black holes seem to be bluer and span a lower galaxy mass range. And so what this is showing is that the iron 10 selected black holes are really picking up a new population of dwarf galaxies that are, or black holes in dwarf galaxies that are inaccessible with traditional optical methods. And because most dwarf galaxies are actively forming stars, these population is also a little more representative. So in summary, today I presented my first systematic search for the coronal line iron 10 in dwarf galaxies, and I identified 81 dwarfs with supermassive black holes using this technique. These black holes represent a new population that is inaccessible with traditional optical methods. And because they're more representative of the population overall, they provide new and strong constraints on the origins of supermassive black holes. Thank you.
Wonderful. All right. Thank you so much, all of you. And we'll go ahead and move into the Q&A session now.
All right, I'm going to be reading the questions that come up in the Q&A feature, and I am going to read them in order of most upvoted. So if you're really eager to see something answered, go ahead and upvote that. So our first question comes from Ethan Siegel of Starts with a Bang, and this question is for Jessica. With the C+ deficit confirmed not only for the galaxies with the highest infrared luminosities, just moved around, sorry, after my comment about the upvoting, but even within an individual galaxy where the infrared luminosity varies, can we draw conclusions about C+ perhaps not being a primary contributor to the cooling of the ISM? If it isn't C+, do we have ideas of what could be responsible for the cooling of these galaxies?
Yeah, this is a great question. Thanks for asking. There's a few different proposals for what's causing the C+ deficit. One of them is that neutral oxygen becomes the primary cooling channel in these ultraluminous galaxies, although there are reasons to question that as well. There's also ideas that maybe it's not that C+ is a less efficient coolant, but that these galaxies aren't being heated as efficiently. So it's something that's kind of changing on the other end. So C+ is doing fine in cooling, but maybe some other property of these galaxies means that as we dump more energy into the interstellar medium, that's not contributing the same amount of heat as we are seeing in the other galaxies. So there's a few different proposals. It's not necessarily clear which is exactly right, although as we see these different scales, different regimes, we can start to narrow the possibilities down.
Excellent. Our next question is for Yuanze from Govert Schilling, freelance. Is our Milky Way galaxy red or blue, and has it experienced or will it experience a quenching phase?
Thank you for the question. So it's actually either red or blue. We call it green, and it is actually experiencing its quenching phase. So its star formation rate is declining.
Thank you. Our next question comes from Ethan Siegel at Starts with a Bang. This question is from Mallory. Many of your blue galaxies from a visual inspection look like they're being tidally disrupted in some sense. Is there a connection between iron 10, star formation rate, the blue color, and whether a galaxy has a large nearby massive neighbor?
So those are really good questions. I do not know if there is any specific connection. This was kind of a new thing that we discovered, that we could actually detect iron 10. I will say that most of the objects, I don't know if they're necessarily tidally disrupted or if they're just irregular, because dwarfs tend to be kind of weird in their shapes. So that is something that we plan on looking into a bit more. And then in terms of the connection between iron 10 and star formation, I don't know if there is a correlation. We're planning on doing more kind of follow-up work to try to figure that out. So I have a lot of like follow-up observations planned to kind of figure out what is, to confirm the presence of the black hole, to look at the interaction between the black hole and the host galaxy, which might give us a little more information on the question that you have.
Thank you. Our next question comes from Rick Feinberg at the AAS for Ryan and Mallory. Combining your results, do you have a sense of whether they favor one model of black hole formation over the other two?
Do you want to go first, or?
Sure, maybe I'll start that one. Thank you, Rick, for this question. I think I would say, and Mallory, you can correct me if I'm wrong, but I would say that the work between our two studies does not. I think it points in the same direction, but it doesn't necessarily make a clear conclusion either way. So really, as mentioned early on, the question about what the seeds are. One observational tool we have is the fraction of galaxies as a function of their mass that host black holes with some given mass. So it's really the relationship between galaxy mass and black hole mass. And looking at AGN in the way that we have is one way to find those. So in a way, they give you a lower limit on how many of such dwarf galaxies could actually have black holes in them. So the more of them you find, sort of the larger you raise that lower limit. And if you get up to a really high number, then you start saying, okay, the conditions are for making direct collapse black holes are too rare and too sort of finely tuned in most models to produce so many direct collapse black holes in these dwarf galaxies. And so therefore it must have been some other mechanism like runaway collapse or just building up on stellar seeds. And so I think there's a lot of uncertainties because we don't know what fraction of the black holes that are there are actually accreting. And so converting a number of AGN that we see to a number of actual black holes in those galaxies still requires some assumptions and is going to take a lot of work. But I think both of our results suggest that there are more of those accreting black holes than we have been able to find previously, which sort of points us closer in the direction of there being smaller seeds, but is not at all definitive.
Yeah, I would agree with that. And I would also say that I think this is a question that will be kind of re-explored, especially with JWST and LISA. These new surveys are going to provide a wealth of information that will really help kind of nail down this question a little better. I think right now we're all kind of holding our breath, waiting for these new telescopes and trying to find new ways to find these black holes, but we're kind of reaching a limit of what we can do with traditional methods that we're using right now. So it'll be exciting to see where this field will go when these new telescopes are ready to go and being used.
Great. Another quick follow-up question for Mallory from Rick Feinberg again. How many dwarf galaxies did you examine to find the 81 black holes? Was it 100, 1,000, 10,000?
Yeah, I think it was around 40,000, something like that. It was a very large number. I was honestly surprised that I was able to find 81. Iron 10 is naturally a very weak line. And this 3 arcsecond spectrum SDSS fiber that I was using is pretty large on a dwarf galaxy, if you think about it. So the Iron 10 had to be really strong and fight over the signal from that host galaxy in order to be detected, even at somewhat weak signal to noise of around 2 to 3. So I think that it's definitely also a kind of tip of the iceberg thing. I think if we had higher resolution data, I could have found more. But with the survey data, I was really happy to find 81 even out of like 40,000.
Great. Our next question comes from Bill Waller at the Galactic Inquirer, and this question is for Jessica. Could the C+ emission anti-correlate with H alpha and other tracers of ionized gas?
So C+ actually typically directly correlates with H alpha, since H alpha is a tracer of star formation rate often. So because we hope that we can use this, there have been studies that have looked at this comparison and see that it's pretty well correlated, although in the more luminous galaxies that have the deficit, we start to see kind of a flattening off. One of the issues with H alpha is that it's an optical emission line, so it can be blocked by dust in a galaxy, whereas C+ is a far infrared line that typically isn't going to be attenuated by dust. So that also changes this relationship a little bit as well. So when we look at the C+ from the neutral and ionized, we compare more to ionized nitrogen emission, the 205 micron line specifically, which won't have those attenuation issues and and can only be produced by the ionized gas.
A question again for Mallory. From Gubbert Schilling, freelancer, what percentage of dwarf galaxies are expected to host black holes? And what about the well-known dwarf galaxies like the Magellanic Clouds or the companions of M31?
So I know that how many dwarf galaxies host black holes is kind of the $1 million question in this field. I think we all wish we knew the answer, because then we could know a lot more about how black hole seeding works. We could also actually use it to study how dwarf galaxies evolve with their black holes. There's a lot of interesting things that we could learn if we knew the fraction. Unfortunately, we don't. And then in terms of M31 and its satellite galaxies, I don't remember if they have a black hole. I don't study them. I think that they do, but I don't remember off the top of my head. Maybe you know, Ryan?
Yeah, M31 does, of course. It's a big galaxy like the Milky Way, so it has a big one. But as far as I know, none of the satellites that we know of in the local group have an obvious sort of middleweight black hole with an AGN in it. So that's actually I think kind of an important constraint. Whether or not for a lot of these, I think it would be challenging to detect them using dynamical techniques even. So looking for the orbits of stars around them, even if they weren't accreting. So we don't really know at the moment, I think what the black hole occupation fraction is, even in the local galaxy. But the ones that we study that are you can see, but because they're accreting, we don't know of any of those in 100,000 solar mass black holes actually in our own local group, unless one was recently discovered. But that's my understanding.
I have a question here for Ryan from George Musser, freelance. Why should direct collapse be rarer than other supermassive black hole formation mechanisms? And what do you conclude about these mechanisms from your study of Markarian 462?
That's a great question. Yeah, I didn't get into any detail as to why this is actually the case. So to make a direct collapse black hole turns out to be pretty hard. What you're doing is trying to take a large amount of gas, 100,000 solar masses of gas, and squish it into a very small space that's significantly smaller than the solar system. So how is it that you actually drive all that stuff down to the center of the galaxy effectively in one go? If you were to have a cloud like that in the local universe, in some nearby object, there's no way that process would happen, because it would cool and fragment and then form individual stars or individual clumps all over the place. Now, in the early universe, turns out there were conditions that, if everything is exactly right, can make it so that kind of cooling on smaller scales is inefficient. So the galaxy sort of retains its thermal energy and it can actually just all collapse in under gravity. And that's because the gas was more pristine. So there were very fewer heavy elements, which are good for producing cooling. And there are also potentially radiation fields of high energy photons that can break apart molecular gas, molecular hydrogen in particular. So if molecular hydrogen starts to form, that then is really good at cooling and would again cool down and fragment. But if it's getting hit by this high energy radiation field, it's called Lyman-Werner radiation, then that cooling process can be shut down. And so those conditions are what you need in order to have this large amount of gas squished into a small space in the early universe. And how common that is, and this is again one of the uncertainties that we deal with, is how common that is still pretty uncertain depending on what exact model you use. But it's almost certainly less common than just making a massive star that can then blow up and turn into a black hole. And that, you would expect that to happen in pretty much every galaxy. So so our results by themselves don't really tell us anything. The fact that we know that there's this obscured AGN in Markarian 462 tells us that there's an obscured AGN in Markarian 462. But the one thing that it does tell us, I think, beyond that, with not too much extrapolation, is that these heavily obscured AGN, like the ones we see for the more massive systems, do exist, even in these small black holes. And we know, again, that most of the really massive black holes that are accreting actually have a lot of material around them, make them hard to see. And so if you do an extrapolation, that tells you that there could be significantly more growing black holes than we already know about in these dwarf galaxies. Whether it's enough to definitely say that we don't have a direct collapse scenario as the dominant scenario. I think we're not there yet, but it's kind of trending in that direction.
Great, thank you. A question for Jessica from Liza Sazanova, I believe from Johns Hopkins University, but feel free to correct me if that affiliation is not right. Can simulated galaxies help you understand how C+ changes with galaxy orientation?
Absolutely. Simulations are incredible, and the models we have are just always constantly blowing my mind. So they can definitely be helpful. The issue is that some of the causes of the C+ deficit and things like that are really dependent on the microphysics within the interstellar medium. So where electrons are coming from, how fast are they moving, what's heating them, how many are coming from hydrogen versus how many are coming from dust grains. And those things can be those very small details can be difficult to model in these big simulated galaxies. So codes that specifically deal with modeling the interstellar medium and trying to produce the spectra we would expect to see from a galaxy based on those conditions have been really helpful in trying to understand what can cause the C+ emission to be brighter or fainter. But since there's still a lot we don't know on these kind of very small scales, it can be difficult to determine which scenario these codes put forward is exactly accurate.
Question from Bill Waller at the Galactic Inquirer for Ryan. Does the AGN's total luminosity in the galaxy you studied follow the total luminosity versus spheroid mass trend found by Cormandy, et cetera?
That's a great question. Thank you, Bill. And it's a little bit tricky to answer, but the answer is roughly yes. So we have, what we don't have for this object is any dynamical mass estimate for the black hole. So we don't have we don't see that, we're not able to resolve the stars going right around the black hole, and we're not able to, there's no broad emission lines that we could use to actually study the velocity of gas that's going around the black hole. So we don't have a direct measurement of the black hole's mass, which meant we were left actually to get that number of 200,000 solar masses I told you. We actually sort of inverted it and did a study of the properties of the stars in the galaxy and said, if it was sitting on the relationship that we know between galaxies and black holes, this is what the approximate black hole mass would be. So that's kind of, hopefully that roughly answers the question, which is that it is because we assumed that it is. But there's also a good way to, we have some confirmation of that. And that's due to the fact that we see a large total luminosity for this source relative to what you would expect for, say, stellar processes and other things. So we can use the X-rays and the infrared and some of the other indicators and the visible other indicators we have to estimate what's the total AGN luminosity from this object. And we can compare that to what the maximum luminosity that the black hole could have if it has a mass of 200,000 solar masses. So this is something called the Eddington limit. If the black hole has a certain mass, if it gets too luminous, it would actually blow away all the material around it, and that would overcome the force of gravity. So we know what that limit is. And it turns out that this black hole, if we assume it's 200,000 solar masses, is accreting at roughly 10% of its maximum rate, which is exactly what you expect given our models for how black hole accretion works, given the signatures that we see from the in the radiation, particularly in the X-rays and the infrared, actually, and the optical as well. So we only have an indirect estimate. One thing that does do is gives us a lower limit on the black hole mass, because it can't be any less massive than around, 20,000 times the mass of the sun, because if it were less than that, then it would be accreting at a higher luminosity than the Eddington limit. But that's really rare to find extremely high accretion rate sources. And so we think the fact that it's 10% seems to match pretty well with it being on this relationship between black hole mass and galaxy mass.
All right, we've got a couple more questions that we can try to squeeze into our last minute or two here. For Mallory from Keona Smith, freelance, what does this population of black holes suggest about black hole formation in the early universe?
Yeah, so that's a really good question. I think Ryan and I have kind of addressed it in various different questions. I do think that it doesn't necessarily tell us exactly how black holes are forming in the early universe, like what seeding mechanism, for example, like Ryan talked about. I do think what it tells us is that the way that we traditionally search for black holes in massive galaxies are only basically finding the most easiest to find black holes in dwarf galaxies. And that by adopting these new techniques, you can kind of understand that it's not just the very massive red end of the dwarf galaxy population that hosts the black holes. You can also find black holes in less massive galaxies that have a lot of ongoing star formation. So I think it basically says that there are more black holes than necessarily meets the eye with traditional optical techniques. And that can, I guess, kind of hints that smaller seeds might be a more reasonable scenario for formation in the early universe.
Great, thanks. And do we have time for our final question? Okay, great. This question is for Ryan from Ethan Siegel of Starts with a Bang. After talking about the speculative direct collapse scenario to form 100,000 solar mass black holes in the very early universe, you mentioned that seeing supermassive black holes in dwarf galaxies could provide evidence for that scenario. That seems like there are clouds on Venus, so maybe there are dinosaurs on the surface leap. I know you were limited in the amount of time you had to draw that connection, but could you explain why this link might not be as speculative as perhaps one might think?
Thank you, Ethan, for that question. And this is one that I think touches on the challenge of trying to understand this process, especially from looking at things right around us. I would say maybe it's not quite, at least my own feeling, it's not quite as speculative, as going from clouds to dinosaurs, but maybe it's more like saying there are birds on, I see an ostrich on the Earth now, and so there must have been a dinosaur that it evolved from, or something like that. But the idea is that the nice thing about black holes, one thing that's really nice about them is that they stay black holes. So they don't turn into anything else. So if you have a black hole early on, it will remain a black hole later. And the only difference is how much mass it has by how much mass it has accreted or how many other black holes it's merged with over time. And so we have a pretty good sense that the black holes that we see in the universe now must have formed, or must have also been black holes earlier in the universe. And the question is sort of what was the overall path of that evolution that we have. And I think the main distinction here, again, has to do with not so much the existence of any individual black hole, but the fraction of galaxies that host ones of different mass. And along with that is kind of the assumption that the same physics is kind of happening everywhere in the universe, roughly. So if you have some dwarf galaxies that had a small black hole that then could turn into a big one via mergers and accretion processes, then you'd expect that to kind of happen all over the place. And so if you see big black holes all over the place now, then that tells you actually they probably didn't form from a rare process like direct collapse. The inverse is, but the one challenge is that you have to invoke some other interesting and kind of unusual physics to really get that to work. The flip side is if you only see black holes like these in a handful of galaxies, and maybe you could even look at the properties of those galaxies that we see, that might then actually tell you, well, it's a rare process, and so the sort of most obvious rare process is this direct collapse scenario. But I don't think, one thing to say is that I don't think just looking at these local galaxies in the way that Mallory and I and Jack, my student, are doing is really going to answer the question entirely. To really do it, you need to be able to actually watch the formation of these things in the early universe directly. And as Mallory mentioned, James Webb is going to start detecting these small galaxies and possibly some of these small black holes. LISA will actually watch these black holes merging with each other, which will be really amazing. And ultimately, if we have something like a flagship X-ray observatory, which is one of the things that was recommended in the long term potentially from the Astro 2020 Decadal Survey, that would then allow you to actually see the X-rays from these very faint sources really, really early in the universe. And I think probably answering this question definitively is going to take that direct measurement. All the stuff we're doing in the local universe will sort of help point us in that direction.
Wonderful. Well, thanks for wrapping that up with a positive look to the future. I like that. And thank you so much to all of our presenters for starting off this program with a bang. This was great. Thank you to the audience for being here. And thank you to the public information officers who helped make all the press releases happen and help with the briefing prep. Very much appreciated. And also thank you to USRA, who we believe are still sponsoring this press conference despite the cancellation of the meeting. So very much appreciated. One announcement for tomorrow morning, the press conference that was slated for 10:15 a.m. Mountain Time tomorrow morning, unfortunately is a no-go. That's been canceled. But we hope that maybe it will be possible to have that as a standalone press conference in the future. That was the Satellite Constellations and Dark and Quiet Skies press conference. So for now, we will see you all back again, hopefully this afternoon or later today, for those of you for whom it's already afternoon, at 2:15 Mountain Time for black holes and transient phenomena.